Great. Okay, so thank you, and thanks for the great discussion in the previous session. So as Susan mentioned, we've kind of been dividing our meetings in our group half between kind of a journal club format and then half working on a very specific project that kind of arose in the context of generating simulations for a number of experiments, and that is development of the galactic emission models in the Python sky model. And so I'm presenting kind of the work that we have done on that on behalf of the group, but I definitely want to acknowledge people like Andrea Zonka and Ben Thorne and Giuseppe Puglisi and others who have really done the lion's share of the actual coding and development of these things. So I'll explain a bit more what I mean as I go. Okay, so what is the Python sky model? So the idea is that we'd really like to have a user-friendly interface to multi-frequency full sky models of galactic emission, such that, if I want to do some forecasting work or whatever, I'm able to generate a full sky realization of the galaxy at whatever frequency I want. And the code also could handle band passes and beams. This is really thinking about doing a mock observation of the sky with some specific experiment. And in particular, this is models of galactic emission. So it's intended to be integrated with the extragalactic components, which are not included here. So, the cosmic infrared background, zodiacal light, or, even things like the interdimensional noise, the atmospheric noise, and all that should be considered separate to what we're trying to do here. And what we want to provide is a suite of models that kind of span a space in terms of complexity in the foreground properties, whether that means frequency space complexity, spatial distribution complexity, or both. And so, this framework and frameworks like it have been very useful in doing forecasting, as well as trying to make design decisions for experiments, and validating that indeed the cosmology goals can be achieved even if the foregrounds are complicated. And it's also a nice testing ground for component separation algorithms. So just to reference a little bit what Duncan was talking about earlier, it seems that this PySM way of thinking about it and the Cosmoglobe sky model are two kind of different ways of tackling this particular problem from different angles that will suit different needs. So what we're really thinking about here is developing a suite of physically motivated models that have very specific predictions for things like the frequency dependence of the foregrounds and the correlations across frequencies, the spatial distribution of the foregrounds, what the power spectra look like, et cetera. And to be able to choose from a menu of these models, that way you can isolate the particular complexities, things like frequency decorrelation, to identify the impact of particular complexities on the results, so on your final parameter constraints, for instance. Whereas it seems like the Cosmoglobe sky model is really thinking about sampling sky emission posteriors from a component separated fit. And so this is a very nice way to constrain the amount of foreground emission from a particular component, even say, at every region on the sky. So certainly every model generated by something like PySM ought to be consistent within the posteriors that have been derived through the Cosmoglobe framework. But what is different is that you are only kind of sampling at the edge of current knowledge, whereas PySM, really thinking about what physical complexities might be lurking there that we don't have the sensitivity to detect yet, and what are the underlying physical theories that will connect emission across pixels or across frequencies in ways that wouldn't necessarily emerge naturally from a draw from a global posterior. So I think these two things are highly complementary and interface at a number of places. But I'll be focusing here on developing the PySM framework. So kind of a little bit of the history of this is that it was really the legacies from the Planck sky model. So in 2017, Ben Thoren led the development of this PySM2, which is a Pythonic interface using state-of-the-art templates from Planck and WMAP and others to generate realizations of galactic emission that matched what we could measure with the data and then extrapolated in the regimes that we couldn't measure. So the PySM3 is an update to Ben's PySM2. Essentially, the idea would be that all the foreground models that were available in PySM2 are available in PySM3, and then we're going to implement a new suite of them, updating a lot of the templates that were used to the latest and greatest data products. And I believe Andrea also did a lot of refactoring of the PySM2 code to improve things like speed and memory usage and all that good stuff. So it's really Andrea Zonka who's so far been the lead developer of the PySM3 code. And then recently, we've gotten involved kind of as our group because now that the code is in a good and stable place software-wise, what we really want to do is to expand the model library. And so it made sense to pull the assembled expertise to think about, from a galactic science perspective, what are the things, the aspects of galactic emission that we want to be sure are encapsulated by our models that may have relevance for CMB component separation, foreground mitigation. And so the idea is to leverage this expertise to make sure that we're doing good ISM physics and while also meeting the needs of the CMB community. And so this is particularly pressing because there's a number of major simulation efforts underway, particularly CBS4, Lightbird, also SO. And so we want to be sure to have assembled a suite of updated foreground models. That way, any potential snags can be identified early, or certainly want to be using the best available foreground models that we could for the purpose of these very large simulation efforts. One way of thinking about this that is not universally beloved, but potentially useful, is that you want to have a rich model suite that you can pick from to decide what you want to simulate. And you might want to have one of kind of 3 tiers of models. So one being an optimistic model, which is essentially what is the simplest model that you can construct while you're still consistent with current data. So this is kind of like, we know that galactic foregrounds must be at least this complicated, so you should at least be clearing this hurdle in doing the analysis. And then you probably want something that realistic or baseline or whatever the right word there is, that basically where all of the effects that we can think of that we know have to be there at some level are incorporated there at some level. So things like frequency decorrelation, things like small scale non-Gaussianity, things that we know that the real sky has to be doing. And so we want to be sure that the models that we generate have at least some level of these kind of effects. And then you can even think about a pessimistic model, which is where you really open up the theory can of worms and start worrying about complexities that might be lurking there, but we haven't established yet. So these are things like the AME polarization or magnetic dipole radiation from dust grains, things like that. It would be really great if those things weren't in the sky, but they might be, and we might have to deal with them. So it would be good to at least have a way of simulating that so that we can assess the impacts of those things. And so the specific areas of improvement that we've been working on in the group that I wanted to advertise today are one, the use of updated templates. Two is the non-Gaussian small scales. I'll say a little bit about a new module that Giuseppe Puglisi has developed, implementing CO, line emission, and polarization. And then finally, doing multi-layer modeling. So the original PySM2 templates were based on combinations of Planck WMAP and Haslam data. So, to get a pure template of galactic emission, some amount of component separation is going to be required. And so one of the big changes that we've made in the latest iteration is moving to the GNILC dust template maps, just because there was a concerted effort there to do the separation between the cosmic infrared background and the galactic dust component. And since the cosmic infrared background is implemented separately in these simulation suites using, I think most folks are using the WebSky simulations, we want to be sure that we're not double counting CIB by having templates that have CIB in them. So we're migrating over to the GNOTE templates, which have a large level of CIB cleaning. And this is just a general part of an effort to make sure that we're using the best available data product for each of our emission components. And so also on that line of reasoning, the PySM2 code was using a free template that was based on the Commander 2015 component separation, so a full sky map of the emission measure that you can see up there on the top right. Recently, there's been an effort to synthesize that emission measure determination with Faraday rotation data. So this is work by Sebastian Huschenreiter and Thorsten Ensslin from just last year. And what we find is this improves the commander emission measures in well-defined ways, particularly at high latitudes, where you can see that there's a bit of point source contamination in the commander map that goes away when the analysis is done jointly with the Faraday rotation data. So we're working to implement this new emission measure map into PySM. I should also say that Commander actually does a much better job of this by itself on the galactic plane, but we are trading the galactic plane fidelity for the high latitude fidelity in this particular trade-off. Okay. The next item is the non-Gaussian small scales. So the original implementation in PySM2 was, were the scales that are not constrained by data to essentially just fit the power spectra and then generate Gaussian random fluctuations to as small L as you need. And there are two problems with this. And one is that the temperature and polarization were not properly coupled, so you didn't get good TE correlations that match what we see in real data at small scales. And then, of course, the small scales are perfectly Gaussian by construction, which for certain applications like CMP lensing might be an issue. You're overly idealizing your foregrounds, and we know that the galaxy is non-Gaussian. And expect the small scale fluctuations to be non-Gaussian. And so we think that this would paint an overly optimistic picture of the foreground complexity at small scales. And so the solution that we've decided on for implementing the small scales in a non-Gaussian way, at least for now, I view this as kind of a first step, is this polarization fraction tensor framework that Marius talked a little bit about yesterday. And so the idea here is to do a simple transformation, an invertible transformation to these polarization fraction tensor quantities, and this little I, Q, and U, where the I is mostly just the log of the I map, but then the Q and U reduced quantities have the original Q and U, but then modulated by the polarized intensity. And so what this effectively is doing, at least in polarization, is saying that the fluctuations are actually coming from things like the magnetic field orientation. So taking out the density field dependence of this. And then one can more justifiably approximate these fluctuations in these reduced Q and U quantities as Gaussian. So the idea is to transform to these quantities, add the Gaussian fluctuations, and then transform back. And because the inverse transformation involves exponentiation, the fluctuations that are Gaussian in these reduced variables have some level of non-Gaussianity in the transformed variables. And this also naturally introduces the modulation of the polarization fluctuations by the intensity, which is what we would expect physically. So, this is, in some sense, there's a nice physical motivation for this particular framework in terms of thinking about fluctuations in magnetic field orientation. But I think we could do a lot better in the future. And so one way of thinking about doing this is to characterize or learn the non-Gaussian statistics where they can be measured and extrapolate to where they can't be. So this is things like these machine learning models from these papers mentioned here, where we take, characterize the non-Gaussianity over the range of scales that we are able to measure using a neural network, and then making sure that we can do extrapolation from scales we can measure to scales that we can measure. So teach the neural network that mapping, and then have the neural network do the extrapolation from scales that we can measure to then scales that we can't. There's also an idea of using more elaborate summary statistics to characterize the non-Gaussianity that might be able to be extrapolated in physically reasonable ways to small scales. Another potential idea is, rather than trying to do this purely from a data-driven point of view, to think about using MHD simulations where you're getting physical small-scale non-Gaussianity just from the inherent MHD physics in the simulation. And so then maybe one could use either the neural net approach or the summary statistics approach to learn what's going on in these MHD simulations, and then applying that to the data simulations. And then finally, there's, in addition to MHD simulations being able to go to small scales, one could imagine using ancillary data that has higher resolution out of the box. So something like H1 data or the WISE data that we mentioned, measuring what the small scales are doing in those data, and then reapplying that to the emission at the CMB frequencies. So I think there's a lot of R&D work to be done here, but we already have something that is able to at least introduce some small-scale non-Gaussianity that has some physical motivation. So I mentioned I wanted to say just a little bit about CO line. So this is new to PySM 3. So this is based on the Commander CO maps. And then kind of supplemented, so learning a little bit about the statistics of the CO emission, and kind of extrapolating that to high galactic latitudes. It's kind of a mock catalog where we haven't really been able to measure CO emission. And the very nice thing about this is not only is this doing CO emission in total intensity, but also in polarization, since CO line emission can be polarized at roughly the % level due to the Goldreich-Kalafis effect. And so Giuseppe has implemented this framework to be able to do both the intensity and polarization of CO over the full sky. And so we can think about doing similar sorts of things to model CO where we can't measure it. So doing some combination of looking at the spatial statistics of H1 emission and dust emission and CO emission and what their interrelation is. Potentially something could be learned by a neural network and then predicted to make it either go to small scales or regions of the sky that are too diffuse to be able to detect the CO emission directly. And so Giuseppe has done some initial work on this, and it seems promising. So very much in the same spirit that we will be able to use these neural nets to generate small scales, also it looks like we'll be able to use them in the CO emission as well. Okay, and then the final thing I want to talk about is the multi-layer modeling. And I feel like this one is particularly important because it gets to things that can cause problems both for parametric and non-parametric component separation methods. So even if our parametric models of dust and synchrotron are completely perfect. You know, dust is a modified black body intrinsically, and synchrotron is a power law intrinsically. If the spectral parameters are varying, and then you're doing an integration either in a beam or along a line of sight, then all of a sudden your intrinsically perfect SED model is no longer perfect just from the effects of summing things up. So the sum of modified black bodies is not a modified black body. And further, you know, we know that the interstellar medium is 3D. We have things like, you know, dust temperature varying, you know, through the galaxy with galactic scale height, et cetera. And now there's even evidence in Planck data that the spectral parameters are varying along the line of sight as well. So there were Vincent Pelgrim's et al. From earlier this year. Maybe we'll hear a little bit about that later today. And so, you know, we're already at the level that we're seeing these sorts of 3D effects from variation of spectral parameters. And so the goal for us is to build on this very nice 3D layer model by Martinez Soleche et al. 2018 MKD with Jacques Delabrie. And introduce these effects into the PySM framework. And so this 3D layer model is based on 3D dust extinction maps and a model of the galactic magnetic field. And so we should be able to incorporate something like that into PySM, on top of which we can paint different spectral models of dust. Also some interest in doing a similar thing, but using an H1 layer model instead of a dust extinction layer model. And the nice thing about this is that it produces the realistic departures from these idealized frequency dependence, and it also gives rise to frequency decorrelation at levels that we might predict given what the 3D structure of the ISM look like. So this is currently under development, and we've kind of all coalesced in agreement that this should be a high priority thing that we would really like to have in place for the next round of SIMs. Okay, so looking ahead where we are and where we're going, so we've already have updated most of these data templates in PySM. We've implemented this polarization fraction tensor framework to do the Nongaussian small scales. So that is done. Modulo, we're having a little bit of trouble with the fluctuations in temperature in particular, just because you can't assume the same sizes of fluctuations over the full sky, since there's so much dynamic range and the amount of dust emission that you get going from regions close to the plane to high galactic latitudes. So there's still some ironing out of the temperature fluctuations at small scales that we're looking into. And so once that is in place, the next milestone will be to focus our attentions on this multi-layer modeling to capture these line of sight integration effects. And so, as I mentioned, this is actively being developed on the PanX Galactic Science calls. And I just wanted to say, I think these have been really productive to just have a group of experts in the same room or Zoom room, exchanging ideas and discussing this. I think it's been very useful for charting a path forward. So potential discussion topics, and we certainly don't have to discuss these in particular, but just to throw things out, is the model library that we constructed sufficient? Are there any other components or effects that we should be taking into account that we aren't? If you've used PySM, is the software doing everything you want it to? Is there some functionality that you think is missing? And then finally, are there any other data-based templates of galactic emission that we should be aware of and using? And so with that, I think I'll stop and take any questions there might be. So thank you.